So we are going to start with network method in radiation exchange. It's a continuation of what we were discussing in the last class. We have introduced a specific method for solving radiation problems in an enclosure, which is industrially extremely important. So if you want to design a furnace, or if you want to heat any specific object when it's in close proximity of another surface which is at very high temperature, we would like to find out what are the different resistances that the radiative heat transfer is going to encounter. So we have seen that there is something called a surface resistance to radiation, which basically connects the potential, black body potential, and the radiosity. And the radiosity is a combination of the emission part from a surface as well as the reflected part of radiation incident on it. Now, in between two surfaces, there is also going to be the concept of view factor, the amount of energy emitted by one surface, what fraction of that is going to be intercepted by the second surface. So we have seen that surface resistance to radiation, the resistance between two surfaces in terms of view factors, and then again the surface resistance of the surface 2. So we have seen 2 zone enclosures as well as 3 zone enclosures, and it's almost equivalent to the problems of electrical technology which you have done. So you can use the standard techniques, that means the current, the algebraic sum of currents or algebraic sum of heat coming to a node should be equal to 0. So that is used to find out the unknown temperature or the heat flux of a specific surface. That is something else which is known as radiating surface. If a surface is perfectly insulated, then the net amount of heat coming to the surface at steady state would be equal to 0. You are not supplying any heat, nor you are extracting any heat from it. So for that specific surface, even if it's not a black body, the black body potential, that means EB and J of that surface, they are going to be equal. So a radiating surface is a closed node through which no net current can pass. So if you have a closed node like that, then the current coming to that from two sides would be equal to 0. So these are the concepts which we have been exposed to in the last class, which was network method in radiation part 1. In today's class, we are going to introduce a concept of radiation shields, which is extremely important. Now, a radiation shield, as the name suggests, reduces the amount of radiation that a surface receives. It's some sort of an insulation in conduction heat transfer. We know what is insulation. So insulation is used to reduce the amount of heat transfer from or to the surface. Similarly, radiation shields are placed in between two surfaces. Let's say one surface is getting some radiation from surface 1, you would like to reduce that. So what you would do is you would put something equivalent to an insulation, which is a radiation shield in between the two surfaces. Now, when there are two surfaces, we know how the circuit would look like. There's going to be the surface resistance of surface 1, surface resistance of surface 2, and something in between, which is simply going to be 1 by F12, 1 by A1 F12. And if A1 and A2 are equal, it's simply going to be 1 by AF12. What you are planning to do is you are going to introduce one more surface in between the two. And now when you do that, how many extra resistances you are incorporating? 2, because you have two surfaces, surface resistance and the resistance in between the two surfaces, surface resistance here. You introduce another surface, so you are introducing surface resistance on this side and surface resistance on the other side. So those two are the extra resistances that you are incorporating in between two surfaces. So instead of 3 resistances in the series, now you are going to have 5. All right, and this, when I write those resistances in terms of emissivities and view factors, then you would see that you would require some specific property, some specific value of those emissivities. Would it be very high emissivity or low emissivity? That's what we are going to find out. The rest, there is no new concepts involved. It's simply we are placing number of shields in between two surfaces to reduce or to reduce the heat that's coming to another surface. So a radiation shield is nothing but we have two surfaces. The temperature is T1 epsilon 1 and let us say the area is A, and this surface is T2 epsilon 2 and A. So, if I have this one like EB1 and EB2, I am going to have a surface resistance, and this is going to be my J1 as we have done before. This is going to be the surface resistance of surface 2, this is going to be J2, and this we already know it's going to be 1 minus epsilon 1 by A epsilon 1, and since these are two parallel plates, I am assuming that the areas are the same. So, A1 would be equal to A2. Similarly, this is going to be 1 minus epsilon 2 by A epsilon 2, and if we did not have anything in between, then the resistance, the third resistance would be simply 1 by A F12. Okay. Now, I am placing another one in between that I am calling as surface 3, and this has emissivity epsilon 3 facing 1, and this has epsilon 3 facing 2. These are, let us say, these are two different emissivities. The emissivity of surface 3 facing 1 and 3 facing 2, and the area is the same and the temperature is same, some unknown T3. So, what I have is, now I have a J3 facing 1 and EB3, and on this side I have J3 facing surface 2, and that is all. Okay. So, let us see what is the resistance in here. The resistance in here would simply be someone between J1 and J31 is going to be 1 by A epsilon, I am sorry, F1 to 3. Now, between J31 here and EB3, this resistance, it is simply going to be 1 minus epsilon 3 facing 1 divided by A epsilon 3 1. This resistance I am talking about now, that is this one. All of you, is it clear to everyone? All right. Then between EB3, that is this one, and J3, there is another surface resistance which would simply be 1 minus epsilon 3 to A epsilon 3 2, and then I have something from J32 to J2 which would be 1 by A F32. So, that is going to be the two the extra resistances, two extra resistances, this one and this one, which you are incorporating in the series. So, if I am trying to find out what is the total resistance or what is the total amount of heat flow between 1 to 2, it would simply be EB1 minus EB2. That is going to be my driving force, EB1 minus EB2, and EB1 EB2 I can write as that is EB1 and EB2 if the temperatures are T1 and T2, and the sum of all these resistances. So, 1 minus epsilon 1 by A epsilon 1 plus 1 by A F13 Okay. So, if we assume now that epsilon 3 1 and epsilon 3 2 are equal, which is most probably going to be true, because the emissivity on both surfaces of the same surface will probably be the same. So, what I can say then is Q1 would simply be equal to A sigma T1 to the power 4 minus T2 to the power 4 divided by it's just an algebraic simplification, nothing else. A sum of resistances which is due to the first plate, surface resistance of first plate surface resistance of second plate and the resistance in between. The important thing is these two extra resistances, and they will tell us that in order to reduce Q1, which is my primary objective, how do I reduce Q1? In order to reduce Q1, epsilon 31 and epsilon 32 must be small, large, or what? Must be small. So you choose a radiation shield which has very low emissivity. Okay. So emissivity of the radiation shield must be small in order to provide effective resistance to radiative heat transfer between two surfaces. So this simple analysis based on our network analogy would give us the property of a radiation shield, that these should be small enough. And in your text you would see that there are certain, like if you have, instead of one such shield, if you have two such shields in such shield, what would be the relation? That's pretty simple. I am not going to derive that in the class, but the main point is emissivity should be small. Similar to this, there are also few things in your text which again you can look into. That's concentric sphere and concentric long cylinders. So if you have two long cylinders, that's very common, two pipes, two concentric pipes, you are trying to find out what's the total amount of radiative heat transfer in between them. So for two concentric cylinders, there's going to be three resistances, right? If you have one cylinder like this and another cylinder, then you have one surface resistance, second surface resistance, and a resistance in between. Okay. So three resistances in series. Only complicacy that you are going to have is A1 will be different from A2. That's the only difference that you are going to get. Nothing beyond that. Conceptually, it's going to be the same again. That's more or less about network radiation or network method in radiation. I would like to emphasize one thing here. I have introduced you to network method of radiation, but there is something which I haven't taught in this class. If you see, we are restricting ourselves between 2-zone enclosure and 3-zone enclosure. So there can be a case where the zones present in an enclosure is more than 3. Would we be able to solve it using our simple network method? If you have 4 or 5 surfaces which are forming the enclosure, how did you solve the problem in AT? If you have 4, I mean, instead of, if your circuit is more than a star, how could you solve it? Let's think about that. If you have 4 such zones, then it's going to be extremely difficult, because it will look something like each one is going to interact with 3. So this one is going to interact with 1, 2 and 2, 3. So if a problem comes like that, how are you going to solve this? Pardon me? Algebraically, how do you handle such? Because there's going to be a large number of such equations. Can you express based on the concept that the current at each node at steady state would be equal to 0? So how many equations can you write for this system, for this node? How many unknowns are there? You have J1, J2, J3 and J4. Okay. So let's say this is J1. So the current from J2 to J1, 3 to 1 and 4 to 1 all would be 0. So you are going to form an algebraic equation that contains J1, 2, 3 and 4. If you have a very large number of surfaces forming the enclosure, then you have J1 to n, one equation containing J1 to n. So for each of these nodes, you are going to have an algebraic equation involving J1 to n. So you are going to have a series of algebraic equations with number of surfaces. So how do you solve such an equation? You have done numerical methods. You see, you know about it. I can hear the word, but you should be bold enough to. tell me. Matrix inversion. Okay. So then you simply use matrix inversion and find out what are those unknowns J1, J2, J3, J4. Once you know what are the numerical values of J1, J2, J3, etc., then EB1, etc., would be obviously known to you. Suppose using matrix inversion, you know J1, and this is your after one resistance, this is your E1. So if J1 is known, then EB1 can also be found out. Once EB1 is found out, then temperature of 1 can also be found out. So if we go beyond 3, a simple network, instead of using network method, which is very easy to understand and which can be expressed in a pictorial way, you can simply write all the equations for each node, use matrix inversion method to find out what are the unknowns J1, J2, etc., and then knowing each of the radiosities of each of the nodes, you can find out what's the radiation potential of the surface. From that you can find out temperature. Once you have EB1 and J1 known to you, then you also know what is the amount of heat that's coming to node 1 from outside. Is that clear? If I know my J1, I may have thousands of nodes after that, and I know my EB1. So I can find out what is the amount of current or amount of energy that has to be supplied to surface 1 in order to maintain its temperature at a steady value, which is simply going to be EB1 minus J1 divided by whatever be the resistance, surface resistance in between. So knowing this, I can calculate this one. Knowing this, I can calculate T of 1, and if I know these two, I can find out what is the amount of heat that is to be added or extracted from the surface to maintain its temperature at a constant value. So network method is just the initial part for radiation exchange problems. Any complex problems involving more than 3 surfaces has to be solved by matrix inversion method. Then we are going to solve a few problems in the next part of this class, but before that there is another thing which if I do not introduce that, the radiation a study of radiation will be incomplete, which is gaseous radiation. Now what we are assuming so far is that whatever be there in between two surfaces, they are not participating into the radiative process at all. It's as if the two surfaces which are facing each other, there's nothing in between, it's vacuum. But that's not going to be the case in real life. There is going to be some amount of gases or vapors present in between the two surfaces, and those gases and vapors, if they are polar, they are going to absorb some amount of radiative energy. So whatever radiation that's coming from surface 1, before it reaches surface 2, some amount of it is going to get absorbed by the vapor or gas present in it. Now non-polar gases generally behave as if they are totally transparent. So if you have oxygen, if you have nitrogen, then you do not feel that some gases are present in between the two surfaces. Their transmittivity is almost equal to 1. So any energy that comes out of surface 1 is going to be intercepted, is going to reach surface 2. But if you have carbon dioxide or if you have water vapor, two of the things which are very common in nature, if you have water vapor or carbon dioxide, they are going to absorb some amount of energy coming from surface 1 to 2. So the intensity is going to get reduced, and it will depend on the chemical nature of the gas or vapor and how much or what's the thickness of the gas layer in between. So if you have a large thickness of gas or vapor, obviously the amount of intensity reduction would be more, and if you have less, it would be small. If you have a highly polar molecule present in between the two surfaces, they are going to absorb more energy. So this would give rise to the concept of volumetric absorption. The volume of gas or vapor present in between two surfaces is going to absorb some amount of energy. So you would like to find out what is the amount by which the intensity is going to get reduced, and you probably have heard of the name absorption coefficient. Each gas has an absorption coefficient, which is again a spectral property. Okay, it not only depends on the wavelength of radiation that's coming from surface 1, it also depends on temperature as well. So these absorption coefficients of normal gases or many of the gases are already known to us. Okay. So, from that, if you know the temperature and if you know which gas you are dealing with, then you can find out the absorption coefficient. And then if you know what is the thickness of the gas layer in between two surfaces, you would be able to find out what is the intensity of the radiation when it reaches surface 2. Now, anyone who knows the name of the law that would give you the reduction in intensity with distance traveled? Okay, let me just heuristically derive the equation and then maybe you would be able to tell me. Let us say this is my surface 1 which is situated at 0 and this is the x, and I have the second surface at L. I have an intensity of radiation is I lambda, and I would like to find out what is the intensity at this point when it reaches surface 2. I have a participating medium in between, that means the gas present or vapor present is going to absorb some amount of energy. So, let us say I take a very small differential element of gas which is dx in thickness, that is really small, and the radiation intensity over here is simply I lambda and it is a function of x. So, the amount of absorption, intensity absorption by the gas layer of infinitesimal thickness dx will be given by whatever be the absorption coefficient and whatever be the intensity of radiation at that point. Okay. It is a volumetric absorption process. Let us see what I have done. That's the proposal, that's the proposed law. The reduction in intensity due to the presence of this thin layer, infinitesimally thin layer of gas, is going to be proportional to whatever be the intensity of radiation at that point, whatever be the thickness of the gas layer, and the proportionality constant is simply your absorption coefficient. Which is different for different gases. So, that is the proposal. Yes. No, if you have a different, if you have a gas at one temperature and at another temperature, the energy levels are going to be different. The energy levels of the molecules are going to be different. So, they can influence the amount of absorption of radiation by that molecule. So, K infinity though is going to be a weak function of temperature. Mostly it depends on the chemical nature of the molecule that we are dealing with. So, this is what that is proposed for to account for the reduction in intensity. Now, I can always integrate it from this surface which is at x equal to 0 to the surface at a located at a distance L, and I know that the radiation intensity at this coming out of the surface is known to me, which is I lambda 0, and let us say this is I lambda at L. Here I am assuming that this is independent of distance. Okay, that's an assumption. So, I simply have, it's going to be an exponential one. This is going to be the relation, proposed law for volumetric absorption of radiation by a gas which is present in here. So, does this law look familiar to you? You have seen this similar type of law in many other fields of engineering. Okay. A reduction which is exponential in nature. Okay. You must have seen it at different places. I am sure when I write the name, you will definitely not forget it. It is known as Beer's law. Okay. So, that's a famous law for volumetric absorption of radiation. Now, if I look at this one, okay, this is some radiative property. So, Beer will not only give you headache, but will give you some radiative property. Which is that radiative property? Your reduction in your intensity at this point compared to your intensity at this point. So, if you think of the common radiative properties, which one would that be? You measure the you measure the intensity at point this, and you go to this point, the intensity changes, and you come to this point, the intensity is again different. So what is changing? You start with x amount of energy, it passes through this, you receive less than x amount of energy. So which property are you taking care of? You have a blue glass. Okay. You measured whatever be the intensity of the light in normal light at one point. You go to another point in the glass and you measure a different intensity. If you have very dark blue glass, the intensity that you measure at second point would be even lower. So which property am I referring to? Transmittivity. So this is nothing but the transmittivity of the gas layer that we are talking about. The intensity that you get from a thickness of the gas layer, which is L. So this is what you get at the end of the at this end compared to what you start with. So this is nothing but the transmittivity of the gas layer. Now once you know transmittivity, and I can simply say that this is again an assumption that my absorptivity is going to be 1 minus tau lambda, if I assume that the reflective component of the radiation from a gas is extremely small, which is a valid approximation. So this simply follows from our relation that alpha plus tau plus rho would be equal to 0. And if we think that Kirchhoff's law is valid, then my epsilon would simply be equal to epsilon lambda would be equal to alpha lambda, and this is going to be 1 by tau lambda. So Beer's law provides us with an estimate of what's the emissivity of the gas or vapor. Okay. So it not only gives us the transmittivity, you can find out what's the emissivity of this. The last concept is gaseous emission and absorption. And here we see that the amount of energy coming out of a gas at a specific temperature is expressed as epsilon g sigma Tg to the power 4. It's a very common relation. You have a gas at certain temperature, you would like to find out what's the amount of energy that you are going to receive from a gas which is at a very high temperature. You know about the term flue gases, the gas which comes out of a refinery or of a power plant. It's at a very high temperature. You'd like to utilize the heat content of the gas that is coming out. So you'd like to, and at that high temperature, 1000 degree or more than 1000 degree, it's radiation which you would like to capitalize on. So if you would have to find out what is the epsilon g, the emissivity of that gas. Now then you would use a relation which is somewhat similar to Stefan's equation, which is E equal to sigma epsilon sigma T to the power 4. But in the case of gas, this epsilon g is defined in a slightly different way. It's a definition only. The epsilon, the amount of energy which an unit surface would receive if it is placed at the center of a hemispherical gas mass, that is now given by this expression. So if I have a hemispherical gas mass at a temperature Tg and I place a surface over here, then the amount of energy this surface would receive, that is given by this expression. So I cannot do about my Tg, that sigma is a constant. So the definition of epsilon g is given like this: the amount of energy that this surface would receive if it is placed at the center of a hemispherical mass of gas at temperature Tg. That's how epsilon g is defined, and then you know what's the amount of energy or per unit area that's being received by surface 1. Now that's easy to postulate, but how do you find epsilon g? There are different ways, engineering ways of finding epsilon g. They are mostly empirical, experimental in nature. So what was done is you would see a large number of graphs for different gases and vapors. The most common are water, vapor and carbon dioxide. So, for each of them you are going to have different values of epsilon g. Now, let us see what are going to be the dependence of epsilon on various things. So, that means what is going to be the independent variable here, and I am going to say that you are going to get a large number of curves like this. So, you have one independent variable here, another independent variable in this. So, let us try to find out on which this epsilon would depend on. So, your idea is, look at this expression. You have air in which you have some amount of carbon dioxide. Okay. So, you have a hemispherical mass of air, very hot air on a surface. So, this is going to give you the amount of energy that you are receiving. I would like to find out epsilon g. So, what would be the dependence of epsilon g? Gas temperature, fine. So, Tg is definitely going to play a role on epsilon. Anything else? I said, like, we have in air some amount of carbon dioxide. Air doesn't, or nitrogen doesn't take part into this radiation, only carbon dioxide does. So, what would be the other independent variable? Pardon me? Mole fraction of carbon dioxide present in air. Another way of saying the same thing is, what is the partial pressure of carbon dioxide in air, or partial pressure of water in air? It denotes what is the amount of participating medium present in the gas. So, we express it in terms of partial pressure. So, these are for different partial pressures of it can be water, it can be carbon dioxide. But I am one thing is clear, I am talking about when there is only one participating medium in the gas. This is valid when only water is present or only carbon dioxide is present, not when both are present. We will come to that later on. So, this is going to be Pw. And what is this L? I said that gaseous radiation is a volumetric phenomenon. Okay. So, there has to be another independent variable which denotes what is the distance between the two surfaces. That means how much gas or vapor you have in between the two. If you have more gas, the absorption is going to be more. So, this one denotes the amount, and this one denotes the amount of gas that is present. This is Pw is what is the fraction of participating medium, and this is the total amount that is present. So, you have Tg, Pw and L. You can read what is epsilon g for carbon dioxide and for water and for other gases as well. Okay. These all are at 1 atmosphere. That could be another variable. You can have gas which is pressurized, which is not at 1 atmosphere, but higher than 1 atmosphere. So, there has to be a correction factor which can be added to this epsilon for different values of pressure. Okay. You can, I am just drawing it like this, you can see it in your text, is that depending on the pressure that you have, you are going to have a correction factor, and where the epsilon of water, let us say at P not equal to 1 atmosphere is given by a correction factor times epsilon W P equals 1 atmosphere. Let us see, this is empirical. So, let us see how we can do it, how we can perform our engineering calculation. This part, the value of epsilon at 1 atmosphere is obtained from curve number 1. The correction factor is obtained from curve number 2, and the x axis is Pw, that is partial pressure plus total pressure divided by 2. That is how it is expressed in engineering texts. You read the value of this from curve 1, which is at 1 atmosphere, then you introduce a correction factor to find out the epsilon of water vapor, let us say, when the pressure is different from 1 atmosphere, and you read and you evaluate that Cw from a curve like this. Okay. That is how it is done. I mean, it's semi-empirical in nature. The values of epsilons were experimentally calculated and correlated with T partial pressure and distance in between the two. The third only unknown thing that remains here that we haven't discussed is what happens if I have both carbon dioxide and water present in it. So, if I have my epsilon G, that is the equivalent epsilon, is it going to be epsilon water, epsilon carbon dioxide? Is it simply going to be this? That I have an emissivity due to the water molecules present, emissivity due to the carbon dioxide molecules present. Sum them together and I get the total emissivity. Okay. You have 10 molecules of carbon dioxide. You can find out what is epsilon W from our previous discussion at 1 atmosphere and at a pressure different from 1 atmosphere. You have 5 molecules of carbon dioxide. So, you can also find out what is epsilon C from the same set of graphs for carbon dioxide as we have discussed just now. Sum them together and you get the total amount of emission from a gas comprising of carbon dioxide and water. Is there any mistake in there? Are we missing something? Interaction between carbon dioxide and water. And what kind of, because of this interaction, would the emissivity be more or less? Less, because whatever is emitted by, let's say, carbon dioxide, part of it is going to be absorbed by water and so on. So, a correction factor in the form of this delta epsilon is generally subtracted from the sum of these two to find out what would be the effective emissivity of a gas mixture comprising of carbon dioxide and water. And you have another such curve to find out what would be the value of this is the way you would see the curves, the figures in engineering literature. Delta epsilon, the change in epsilon that you have to incorporate in this equation as a function of Pw, Pc and this L at a specific temperature. Okay. If the temperature is different, then you have to use a corresponding that temperature specific to that. So, this is T at equal to T1. This is how you incorporate the radiation when you have more than two gases, more than one gases, participating gases present in it. But there is one thing, the last thing that I would like to discuss is this L. This L is easy to understand if I have two surfaces like this. Okay. Then this L will probably be just the distance between the two. But what if I have an unknown shape like this? Okay. And this unknown shape is radiating, giving radiation to a surface which is neither a sphere or a cube. I also do not know what is going to happen to a sphere. What should be the distance for the case of a sphere or a cube or an arbitrary mass of vapor or a gas when it is interacting radiatively with the surface. So, to take into account those kind of complications, those kind of different geometry, the concept of mean beam length is used. And what is mean beam length? You would like to find out the emissivity of a hemispherical gas mass of radius L. Okay. And if you have a mass of gas or a vapor which is of an arbitrary shape, you find out what is the emissivity, what is the radius of a hemisphere of gas that will have equivalent emissivity as this gas mass, and this radius is your LE. I will repeat it again. This arbitrary shaped gas mass will have some emissivity. Let us say we convert that emissivity to a hemispherical mass of gas having equal emissivity. If that is true, if the emissivities of these two are equal, then the radius of this hemisphere is known as the mean beam length. if emissivity of this hemisphere and emissivity of this, if they are equal, then LE, which is the radius of the hemisphere, is the mean beam length. And you would see that you have a table in your text which gives you the geometry, specific geometry, whatever be the characteristic length and whatever be the mean beam length. So those are already computed and they are listed. So if you have a spherical mass of gas, what is the value of L that you should use for all these graphs? If you have, let's say, a cube radiation to any one of the surfaces, okay, cubical shape of gas mass, then what's going to be the mean beam length that should be used to use with all these graphs? But the conceptually, it's if the emissivity of an arbitrary gas mass is the same as the emissivity of a hemispherical gas mass, then the diameter of radius of that is your LE. So this is how one calculates the gaseous emission and absorption. Beer's law, the method of Hotel, the graphs etc., that's due to the method of HOTTE Hotel, the concept of mean beam length, the concept of interaction between, let's say, carbon dioxide and water vapor, so as to find out what is epsilon. And we would say that it's once we know the transmittivity, we know what's the absorptivity. Using Kirchhoff's law, we know what's the emissivity. That's how we do thermal gaseous emission and absorption. So that's more or less what I wanted to cover in this class, and I will introduce a few problems for you to solve, and maybe we can continue for another 10 minutes, and I'll read certain problems, I'll explain some of the problems and give you the answers. The first problem that we are going to deal with is, let's say we have a cylinder like this. It's a furnace, and this furnace is 0.3 meter long and the diameter is also same. So diameter of the furnace is again 0.3 meter, and you have three surfaces obviously, which is A1 having a temperature of epsilon 1, temperature of T1 and epsilon 1. This surface is, I call it as A3, and this is A2 with a temperature T2 and an emissivity epsilon 2. Okay. It has been mentioned that one end A1 and the lateral surface, which is A3, both are black. So if A1 and A3 are black, then obviously epsilon 1 would be equal to 1 and epsilon 2 would also be equal to 1. It is also mentioned that the third surface, A2, A3 is insulated. Now the temperature T1 is at 500, T2 in Kelvin, T2 is at 400 Kelvin. What you have to find out is, first thing is net radiation heat transfer from each surface, and the second is find out the temperature of surface A3, which is TA3, and it's given that F1 to 3 is 0.172. This value is given. Let's very quickly discuss how we can solve the problem, and then I'll give you the answer. How would the circuit look like? Do we have any surface resistance? Surface A1, it's a black surface, so EB1 would be equal to J1. So this EB1 is equal to J1, and the numerical value of this is going to be sigma T1 to the power 4. The value of T1 is known to you. So this is simply going to be watt per meter square. Now surface 2, in surface 2 is also black, so EB2 would be equal to J2, no surface resistance, and this Eb2 would simply be equal to T2 to the power 4. The value of T2 is known to you. Now we are coming to surf 3. This is J3 and Eb3. What is going to be the relation between J3 and Eb3 for surface 3 if it is insulated? If it is insulated, that means it's a re-radiating surface. No amount of energy is leaving this or entering this. So if you do not have any energy, net energy leaving this surface, then obviously J3 would be equal to Eb3. So J3 is going to be equal to Eb3. Okay. So this is true because the surfaces are black. This is true because the surface is re-radiating, and it's because Q3 is equal to 0. Now then it's very simple. You have 3 resistances, and this is known to you. So you should be able to find out all the resistances. The resistance at this point is going to be 1 by A1 F12. This is going to be 1 by A1 F13, and this is going to be 1 by A2 F23. Okay. Do you agree? Is there any do you understand this? Like between 2 and 3, it's simply going to be this resistance. Your job would be to find out from the known value of F13 what's going to be F12, 1 to 3, 1 to 2. What is going to be F12? 1 minus whatever this thing, because 1 would be 0. And if 2 to 3 you should be able to evaluate. So that part I will leave for you. Now knowing all this, what's going to be your next step? How do you find out the unknown Eb3? Is there any energy that is entering or leaving this circuit? I know that my Q3 is 0, but can I say that Q1 is 0 or Q2 is 0? Q1 and T1 and T2 are at different temperatures. So obviously it's going to receive some amount of energy from here. So in order to maintain temperature of 2 at constant value, you have to extract some amount of energy. Similarly, in order to maintain this 1 at 500, you have to supply some amount of energy, but nothing is happening at 3. All right. So your Q1 you are adding, Q2 you are taking out. All right. So the sum of Q1 and Q2 at steady state would be equal to 0. Because you have Eb1 and Eb2 are at different temperatures, then your Q1 would simply be equal to Eb1 minus Eb2 divided by the sum of all resistances. Is that clear? To maintain it at 500, you have to supply some energy. To maintain it at 400, you are definitely going to extract some amount of energy. So Q1 would be equal to minus Q2, and Q1 would simply be equal to whatever be the potential difference between these 2 points by divided by the sum of resistances. So this one and this one are going to be in series, and the sum of these 2 is in parallel with this one. So you find out what is the equivalent resistance. You already know the numerical value of Eb1 and Eb2. You find out what is Q1. Now once you have Q1, the value of Q1 will be equal to 143.46 watt. Is this energy Q1, is it to be supplied or extracted from 1? So if it is supplied from 1, it has to be extracted from 2 in order to maintain steady state. And so your Q2 would be equal to the same thing with a minus sign, and Q3, since it's insulated, would be equal to 0. All right. The next part, the last part that is remaining is, what is T3? Now what would be the step to find out T3? How do you find T3? What is the prerequisite for finding T3? Eb3 must be known. We know Eb3 is equal to J3, so J3 has to be known to you. Right? So you just have to find out what is the value of J3. Once you know J3, then Eb3 is known, and this is Eb3 is simply going to be sigma T3 to the power 4. Okay. Now this J3, how do you find out? Okay. So current from here to here, the current at this node must be equal to 0. So you have J3 minus J1 divided by A1 F13 plus J3 minus J2 divided by 1 by A2 F23 is equal to 0. Clear? I'll write it over here. So to find J3, what you write is J3 minus J1 divided by 1 by A1 F13 plus J3 minus J1, J2 1 by A2 F23 is equal to 0. Alright. You know the value of J1, J2, these are known to you. You should be able to find out what is J3, and from J3 I know J3 is equal to AB3, so this would be sigma T3 to the power 4, and T3 value of T3 is 422.7 Kelvin. That's the answer. Any conceptual questions? But these things, these problems you have to practice, otherwise there would be a problem that you won't be able to solve it within the stipulated time. Okay, so you have to be very sure about this convention, that when you are doing it, I mean probably you know all of these, but I am still repeating just to make sure that we you have this thing. If this is J3, then J3 minus J1 plus J3 minus J2. Don't write it minus J3 minus J2. That I think you all know about. So the convention is the current from here to here, here to here. The sum of that would be equal to 0. Okay. So make sure which you are putting as a nodal point. You measure current from that nodal point. Sum them, and that's equal to 0. So you should be consistent with that. Any question? Okay. So that would be the end of today's class.